Hi, and welcome to our 7th video on making a simple Hartree-Fock program. In this video, we're going to be studying the S matrix or the overlap matrix. We need to calculate the overlap matrix in order to accurately determine the expectation values of operators such as the Hamiltonian or the Fock operator in our specific basis set. In an ideal basis set, each basis function would be orthonormal to every other basis function in our set. However, for mathematical expediency, we've chosen to use Cartesian Gaussian functions as our basis set. And a Cartesian Gaussian basis function on one atom is not going to be orthogonal, or does not need to be orthogonal, to a Cartesian Gaussian basis function on another atom. In fact, even on the same atom, they don't need to be orthogonal, unlike, say, atomic orbitals, which are naturally orthogonal to each other. So in order to calculate our expectation values, we need to know how much each orbital overlaps with every other orbital in our basis set. In other words, we need to know what the value is for the integral over all space of each basis function times a complex conjugate of another basis function. Now, we're using Cartesian Gaussian basis functions, which are purely real, so we can ignore the complex conjugate part of it, but we still need to be able to evaluate those integrals. There are two properties of Cartesian Gaussians which makes evaluating those integrals particularly simple compared to other possible basis functions. If you remember, the first property of Gaussian functions that makes them easier to evaluate is that they're separable. In other words, we can take our three-dimensional Cartesian Gaussian function and separate it into three one-dimensional functions, say a function of x, y, and z, and then multiply them together. That makes doing the integrals significantly easier. The second thing that makes doing these integrals easier is something called the Gaussian product theorem. Now, the Gaussian product theorem states that if I have a Gaussian centered at point A and another Gaussian with maybe a different exponent centered at point B, that if I multiply those two together, the resulting function of Gaussian A times Gaussian B is yet a third Gaussian centered somewhere between them. So I've tried to illustrate that here, where I have a Gaussian centered at point A, a Gaussian centered at point B, and when I multiply them together, I get a Gaussian in yellow that is equal to the functions A times B. And then once we have created a new Gaussian, taking integrals of Gaussians over all space is particularly trivial because we can evaluate that simply using the fundamental theorem for Gaussian integrals, which states that the integral should be equal to the square root of pi divided by the exponent of the resulting Gaussian. So let's look at the Gaussian product theorem in a little bit more detail. Right? So if I have a Gaussian function centered at A with exponent alpha, and a Gaussian centered at B at exponent beta, and I multiply them together, what I'm going to get is some prefactor and a new Gaussian. And I can take the integral of the new Gaussian just by knowing its exponent, and I'll get the following result for my total overlap integral. And to evaluate that, we simply multiply this out term by term and collect like terms. And what we get is that the new exponent is equal to the sum of the two individual exponents. And the center location is just the geometric mean of them, or the weighted mean. So it's the alpha times A plus beta times B divided by alpha plus beta. And the exponential prefactor is just the a weighted form of the exponent. So we have alpha times beta divided by alpha plus beta. And then Q is equal to A minus B. So it's just the distance between the two individual Gaussians. And this works great, especially when we're dealing with S-type functions, or functions with no angular momentum. But what about Cartesian Gaussian functions where we have polynomials out in front, when we have angular momentum about the x, y, or z axis? It turns out that that gives us a little bit more of a headache, because although I can still take our basis functions and rewrite them in terms of some new Gaussian centered at point P with exponent little p, my functions, I still have these polynomial functions which are hanging out on the outside, which aren't centered at P, and I don't know how to explicitly evaluate that integral. I've drawn that here over on the right-hand side, where I have a Gaussian centered at point B. So this is a D-type orbital. This is an x squared type Gaussian centered at x equals 2 times a Gaussian with a smaller exponent. This is exponent of 1/2 centered at 0. And when I multiply them together, I get the function in yellow, which is centered somewhere about here. There's also this little lobe over here, so it's not a simple Gaussian function, and I can't take its integral as simply the square root of pi over p. And so we need to have a strategy for dealing with these types of integrals. And the strategy that we're going to employ is that we're going to use a helper function. And the helper function that we're going to use is called a Hermit Gaussian. So a Hermit Gaussian is similar to a Cartesian Gaussian. It's still a Gaussian function multiplied by some polynomials. But the coefficients for those polynomials are fixed. And they're fixed so that we obtain Hermit Gaussians defined by the following law. So a Hermit Gaussian of order t is equal to the tth derivative of our Gaussian function with respect to its center location. Right? In other words, I'm going to take the first, the second, the 0th derivative of e to the minus alpha x minus x naught squared with respect to x naught. And that's how we're going to define our Hermit Gaussians. I can make a three-dimensional Gaussian by just multiplying several of these together. These are still separable functions. So I still have a function of x, a function of y, and a function of z. Now it turns out that I can take my Gaussian function that I would get from multiplying two Cartesian Gaussians, and I can express that as a sum of Hermit Gaussian functions. So I have sum over t to some number, which we're going to call t max, of some coefficient times the Hermit polynomial of the tth order. And what's going to determine t max is the total angular momentum I have in these two Gaussian-based functions. And so this sounds rather complicated, and you might be wondering, why would I want to do that? The reason why we want to do this is that for any Hermit Gaussian that's not the 0th order, the integral over all space of that is going to be equal to 0. Or in other words, if I can find the coefficient for the 0th order Hermit Gaussian centered at point P for this multiplication of two Cartesian Gaussians, I can evaluate the integral quite simply just using the Gaussian product theorem. So the way that we're going to do this is we're going to expand these basis functions in terms of Hermit Gaussians, and we're going to use the prescription followed by, or laid out by McMurtry and Davidson in this paper from 1977. This paper uses recursion relations to find out what these coefficients should be. It's relatively straightforward and a little bit tedious, so I'm not going to go into it. Instead, what I'm going to show is an example, and then I'll show you how it's programmed into our code. So let's do it. Let's do an example. And the example that we're going to do is the example we saw in the last slide, which is a Gaussian centered at 2 with angular momentum about the x-axis equal to 2, and a Gaussian centered at 0 with an exponent of 1/2. And so I can use the Gaussian product theorem to determine my location of my new Gaussian function and its new exponent. But I can't use that quite yet to determine what that expansion should be. So here's my Gaussian in orange, my second order Gaussian, Cartesian Gaussian in blue, and the resultant function in yellow. When I look at what I need to do next is to expand them in terms of Hermit Gaussians. And so we know that we're going to be going up to second order in our Hermit Gaussian because our angular momentum of this basis function is 2, our angular momentum of this basis function is 0. And so I can write down what those Hermit Gaussian functions are. So our 0th order Gaussian is going to be e to the minus p x minus p squared. We take the derivative with respect to p the first time, and we're going to get the following Gaussian. We take our second derivative, and we get the following polynomial times the same Gaussian. And now we need to know the coefficient. So we're going to run this through the program, our algorithm, and we get that phi a times phi b can express in the following linear combination of Hermit Gaussians. And so what I've drawn out here in blue is just this function that we originally had, phi a times phi b. And then the orange circles is the expansion of these Hermit Gaussians, which are defined over here. And we can see that they line up perfectly. Now, once I know this coefficient for h naught, and I know my exponent, I can evaluate the total overlap integral quite easily because it's just going to be this coefficient times the square root of pi over p. And that would be the resultant overlap integral for phi a times phi b. And so that's going to be our strategy going forward. We're going to separate three-dimensional Gaussians into three one-dimensional Gaussian functions. We're going to multiply these one-dimensional Cartesian Gaussians together and use the Gaussian product theorem to find the location of our new Gaussian. We're going to express the resulting function as a sum of Hermit Gaussians. And then we're going to evaluate the integral over all space by multiplying the integrals of just the 0th order Hermit Gaussians, which we can evaluate using that simple rule. Okay, that's going to be our strategy. And so if we hop over and look at our code, we can see we've opened up our HF driver function here. And the first thing we do is we take our function S, which is equal to build overlap of our basis functions. That build overlap function, down here, calls the following function, which takes its basis functions as the input. And now what we're going to do is we're going to loop over each basis function. And then in each basis function, we're going to loop over the number of Gaussians in each basis function. So this allows us to do contracted Gaussian functions. And then for each element of NM of our overlap matrix, we're going to calculate what the total overlap is for each of those Gaussian functions. And then we're going to multiply it by our contraction coefficient if we're using contracted Gaussians. And so let's look at this function G overlap, which takes in two primitive Gaussian functions. And if we look at G overlap, there's some stuff here at the beginning which we can effectively ignore. We're going to use this when we calculate our kinetic energy integrals. That just helps us if the angular momentum is less than 0, we're just going to throw it out. And then what we're going to do is we're going to split it up, and we're going to take G prod 1D, which is another function, which is actually going to compute the coefficients of the Hermit Gaussians in terms of these one-dimensional Gaussians. So we're going to separate into X, Y, and Z, and we're going to get return back a matrix, an array of numbers, which are going to be the Hermit Gaussian coefficients. So let's look at G prod 1D. G prod 1D, we're going to reference this McMurtry-Davidson expansion. We're going to use the Gaussian product theorem to figure out what our new little p and our new big P are, so the location and exponent of our new Gaussian. And then we're going to use the recursion relations defined in that paper from 1977. And then we're going to output a vector with the appropriate expansion. Okay? And so we're going to do that for each Gaussian function. We're going to have 3 of those, one for x, y, and z coordinates. We're going to add all of those up for each Gaussian in our basis set. And then at the end of that, we're going to get a matrix, which will return the overlap of each of our Gaussian functions. All right, so that's how we're going to build up our overlap matrix. In the next video, we're going to talk about how to do the kinetic energy matrix. And then we're going to start tackling the difficult problem, which is how do we solve the matrix elements for the Coulomb integrals and the electron-electron repulsion integrals. All right, I hope this video helped you figure out I hope this video helped to explain how our program is calculating the overlap matrix, and I'll see you in the next video.